Okay, so where x is solved the inequality x minus 3 over x plus 4 greater than or equal to x plus 2 over x minus 5. The first thing you do when you solve this type of inequality, which is like what's called a rational inequality, is first rewrite the inequality so that you have 0 on one side of the inequality and the algebraic expression or the rational function on the left. Okay, so rewriting this inequality, we have x minus 3 over x plus 4 minus x plus 2 over x minus 5 greater than or equal to 0. Okay, so that's the equivalent inequality. Next thing to do is identify what's called the related rational function. And so now that we have identified that, our next thing to do is maybe find the zeros or where the rational function is undefined. Okay, so in other words, what we call the critical values. All right, so let's first identify that we have a denominator, two factors and two denominators, x plus 4 and x minus 5. And so we need to figure out where x plus 4 equals 0 and x minus 5 is equal to 0, because these are the values that will make the rational function undefined. So we could see x equals -4 and x equals 5. So that tells us r of x. The rational function r of x is undefined at x equal to -4 and x equal to 5. Okay, so now that we found our critical values that make the rational function undefined, we now find the zeros of the rational function. In other words, we have to solve the rational equation r of x equal to 0. Okay, so r of x equal to 0 means we have x minus 3 over x plus 4 minus x plus 2 over x minus 5 equal to 0. Okay, so now I like to build up the LCD. The LCD is x plus 4 times x minus 5. Okay, so I'm going to take the first fraction, multiply top and bottom of that fraction by x minus 5, so that I get the new fraction here of x minus 3 times x minus 5 all over x plus 4 times x minus 5. Minus, well, that second fraction, I'm gonna so I built it up so it has the LCD. I would have to multiply by x plus 4 on top and bottom. So I would get x plus 2 times x plus 4 all over x plus 4 times x minus 5. So I had to multiply top and bottom by x plus 4, and we get that. Okay, so now that each of these fractions has the LCD, I like to say forget about the denominators, which is basically multiplying through by the least common denominator in the equation. So what we're left with is basically the numerators on top. Okay, and I'm going to go ahead and distribute those numerators because this is x squared minus 5x minus 3x plus 15. And so what is that going to give me? That would give me x squared minus 8x plus 15. And then minus, well, this is x squared plus 4x plus 2x and then plus 8. So then I'm going to get x squared combined in like terms there to get plus 6x plus 8, and this is all equal to 0. I'm going to go ahead and distribute my negative there to get negative x squared minus 8x plus 15 minus x squared minus 6x minus 8 equal to 0. I do have like terms here. My x squares are going to cancel. And then I have a negative 8x and a negative 6x, which will give me negative 14x. Okay, and then 15 and negative 8 will give me a positive 7x. Okay, equal to 0. Now solving this, I put 7x, it should be just 7. Sorry, 15 minus 8 is 7, not 7x. Okay, so solving this, I'll subtract 7 on both sides to get negative 14x equal to negative 7, and then divide by negative 14, which gives me x equal to 1/2. Okay, so we found our critical values. Our critical values are -4, 1/2, and 5. See, what this does is essentially breaks up our number line into some intervals. In other words, here at -4, we know the -4 made the function undefined, so I'd like to use a u there to say that it's undefined. And then at 1/2, we know we got a 0 output. And then at 5, we got another undefined. In other words, the rational function will be undefined. And so in the interval from -infinity to -4, we want to take a test point and evaluate the rational function at the test point to see if it's positive or negative. Likewise, we need to take a test point between -4 and 1/2 and determine if it's positive or negative, and then between 1/2 and 5 to determine if it's positive, negative, and something greater than 5 to determine if it's positive or negative. All right, so I'm going to go ahead and take some test points here. Let's see, I'm going to go ahead and take, say, -5. And between -4 and 1/2, I'm going to say take -2. And between, say, 1/2 and 5, I'm going to take, say, +3. And then something greater than 5, say 6. Okay, so those are my test points. And I'm going to plug these values into my expression. In other words, r of, say, -5. To save some computation time, I already had these calculations, and this is about 7.7, and so that means it's positive here on the interval from -infinity to -4, and then evaluating the rational expression at, say, -2, that would spit out about a -2.5, so that we know it's negative there, and then at the rational function evaluated at 3 would spit out about 2.5, and it's positive there. You can see by the sign. And then finally, plugging in our last test value of 6 equals -7.7. Once again, all I'm doing is plugging those values into the original function, the related rational function, x minus 3 over x plus 4 minus x plus 2 over x minus 5, and that's what we got. Okay, so R6 was -7.7, which means it's negative here. Okay, so now we're pretty much ready to solve the original inequality. We wanted to solve R of x, the related equation, R of x greater than or equal to 0, which in turn, that solution set would imply the solution of x minus 3 over x plus 4 greater than or equal to x plus 2 over x minus 5. Okay, so that solution, our related rational inequality, the solution of that will have the same solution, is equivalent to the solution set of the original inequality. Okay, so what this here just means, we're looking for where this here is positive or 0. Okay, so we can see it's positive on the interval from -infinity to -4, open parentheses on both of those, because we don't want to include -4 because it makes the rational expression undefined. Union, and this is where we could put 1/2, but we will have an open bracket because we include 1/2 because it's 0. It makes the rational function a 0 there. Comma, and then all the way to 5, but we do not include 5, parenthesis. And so that's our solution set. That will satisfy the rational inequality, which in turn satisfies the original inequality. Okay, so how do we solve this using, say, a graphing calculator? Let's go to decimals. So here's decimals. Okay. And so what you're going to do is substitute your related, or input your related rational function, which was x minus 3. Oops. X minus 3. And I think I'll put a fraction first. X minus 3 all over x plus 4 and then minus the second fraction of x plus 2 all over x minus 5. All right, so there is our rational function graph. I'm going to zoom out just a tad there. Okay, and so we could see that we have some critical values here. And in fact, let me just sketch that. That's the vertical line, x equal to -4. Now, of course, algebraically, we probably, unless we didn't do it algebraically, you could probably anticipate what that is by just looking at where the graph is shooting up and shooting down, because we have an asymptote there. I'm going to go ahead and do that and dot it. Okay, and so the next, we know that we had something right here as well, which was at x equal to 5. And then I'm going to make that the same color and dot it as well. Okay, so that's what our graph looked like. Okay, so we were interested in where the related rational expression is greater than or equal to 0. In other words, positive or 0. So we know that if it's positive, that means the graph or the outputs, right? The whole entire graph will have positive outputs, which means it's the portion of the graph that's above the x-axis. So we can see this is going from -infinity to basically the asymptote, which happened at x equal to -4. Okay, likewise, it's positive where it hits this 0 at 0.5, right? 1/2, 0, and then it went from negative to positive, so that we could see that the portion after 0 here is entirely above the x-axis. And so we could see from 0.5 to the asymptote there of 5, 0, if x equal to 5, the entire graph is above the x-axis. And once you pass that vertical asymptote, you see it's entirely below the x-axis. Okay, so that's why we would get the same interval from -infinity to -4 union the half open closed interval from 1/2 to 5. All right, that's it for this video.